Swayam Prabha. Digital India. Educated India.
Okay, yesterday we concluded our discussion on the signal problem, and signal problem means that if we have, let us say, a shear layer forming over, let us say, again a flat plate, and we excite the system at a fixed frequency omega naught, then we wrote psi as a function of x, y and t in terms of 1 over 2 pi, and wrote that unknown in terms of Fourier transform, Fourier Laplace transform. We do that. This is what is assumed that the system responds at the frequency omega naught. This is what we talk about as the signal problem, right. Now, in contrast to this, we could do the full problem. Why we are doing it will immediately explain. The full problem, what we would be doing? Well, instead of writing full problem, let us say we say a full time dependent problem. Now, here we will not make this assumption. So, see, the signal problem assumption comes here in identifying the response to be also at the frequency of omega naught. So, this is the way the link is. If I have a vibrator vibrating at omega naught, response is also omega naught. So, this any spatiotemporal problem, we omit that part of the temporal dependence, we fix it at omega naught t frequency, whereas in the full time dependent problem we do not make such an assumption. So, here what we are going to write? We are going to write in terms of the double Fourier transform, one for the space, one for the time, and then you notice that phi is now a function of y, alpha and omega. Okay. And then we are writing the phase path is like this, and performing the integral over d alpha and d omega. So, why do we do this? That is apparent when you look at the boundary condition that we have. In the boundary condition what we have, of course, once again you take the u velocity as 0 and psi is given like this. What does it mean? Again we have a very localized excitation. So, we are precisely starting our x axis from the location of the exciter itself. That is why we are writing delta x. So, origin is at the exciter. However, look at this function. What is u of t? U of t is a Heaviside function. What does it mean? That the signal, I mean the excitation starts at t equal to 0, before t equal to 0. So, we are also talking about the origin in time, that is given by this u of t, the Heaviside function. And note that we are still exciting the system at frequency omega naught, and we have done this while we are discussing a tutorial on Fourier Laplace transform. So, that is what we are going to do, is we are going to represent the unknown now in terms of two independent variable alpha and omega in the spectral plane. So, this is essentially the idea. Now, that is what we said, that the presence of the Heaviside function u of t ensures that the excitation truly begins at t equal to 0 at the frequency omega naught. Okay. Now, what we notice that u equal to 0 will give us this that you can see, because the u is del chi del y, and this we are doing it at the wall. So, y is equal to 0, and this we are going to get from here 1 over 4 pi square. Well, sorry, this is 2 pi whole square, 2 pi whole square, and 1 each coming from alpha, 1 from this. So, this will be phi. Well, we are differentiating with respect to y. So, the y dependence only comes through this definition of phi. So, this will become nothing but phi prime, and y of course is 0 and alpha omega, and e to the power again we have alpha x minus omega t d alpha d omega. And if this u is equal to 0, then we must have this equal to 0. So, that is what this 88A represents. Okay. Now, what about this condition? This condition, if you recall, we did that. We did that when we talked about the Fourier Laplace transform of harmonic excitation started at t equal to 0. We get 2 parts. If you recall what we had obtained, the if this is the original, this is our original, right? That is what we are talking about. What is its Fourier transform? Its Fourier transform, if you recall, was 1 upon I omega minus omega naught plus a factor, a delta function at omega minus omega naught. Okay. So, this is what we had obtained. So, what happens in the signal problem? What you do? You do this, you ignore this path, but this is there because of finite startup we can see. So, you realize that how important it is for one to understand what is going on here, because at because the finite startup time you are actually invoking the whole range of omega. So, making that signal problem assumption is an assumption, right, while we should have this. That is what we say, that that phi at y equal to 0 for any combination of alpha omega should be some kind of a function which I call it as a boundary condition at the wall, and which is in this case is 1 upon omega I minus omega naught minus. So, there is a minus sign here, and then we have to add that the delta function there. So, this is the interesting part. Why it is interesting part? Because you see, we are looking at stability, and we are now familiar with the dispersion relation. So, we know that in a dynamical system that a priori we do not know what is the what are the eigenvalues, right. So, it may so happen that although we are looking at omega naught, we can also trigger the temporal dependence, which is different than the harmonic input. In the excitation, we should have the frequency dependence, which is other than omega naught, and that part is given by this. Okay. Now, for each of those omegas, we have a corresponding alpha. That is the dispersion relation, right. For every omega, I have a corresponding alpha. So, what happens is, due to this transient startup, I could set up many eigenvalue combinations other than what we have talked about in the signal problem so far, right. So, this is something that we must realize, that this adds not just simple variety to the problem, but it changes the problem qualitatively. This is something we must understand. Without this, I suppose things are going to be quite different, as we will see. We will show you some results, not immediately, but later on when we will revisit the problem. In fact, in anticipation of things to come in future lectures, let me tell you, when we solve this problem, we could see that what is called as a spatiotemporal wavefront. See, this usual signal problem gives rise to Tolman-Schlichting waves. But when we look at the full problem, we will see that ahead of this Tolman-Schlichting wave, there is a very localized wave packet that moves. In fact, to give you an analogy, this spatiotemporal growing wavefront looks almost like your tsunami. If you have noticed, you have read those accounts of the experiences people narrated during tsunami, that you get some episodes where the sea had receded, and after that a huge wave came and everything was there. So, this is something like this. Suppose this what we saw in yesterday's class, that if I create an excitation here, then it would go like this. Now, this is a growing wave front. When you do the full problem, you are going to see that in front there would be a massive packet here, and this peaks. Well, my drawing is imperfect. If this is order 1, this could be order of 1000. So, you are going to get only 1 or 2 massive peaks coming in, and that is precisely what people have noticed. It is one of the way, if you are going around in the beaches and you see all of a sudden sea is receding. So, that is this part, the trough. So, the water goes away, recedes from the beach. That is followed by this massive peak, and this massive peak is actually the wall of water that actually hits. Well, this is something that comes from this part. That is what I said, in anticipation of things to come. Let us keep ourselves alive to this issue. If we do not worry about this, and we now would like to explain the problem in terms of those 2 modes, which fundamental modes which decay with height, will be given by phi 1 and phi 3. It is the same thing. What you do is, now you fix C 1 and C 3 in terms of the new boundary conditions that we have proposed at y equal to 0. And what we find that it would require solving those couple of solutions for u and v condition, and the u and v condition freezes C 1 and C 3, and you can see C 1 comes from here, phi 3 prime 0 divided by this characteristic determinant. One thing I did tell you, we did notice that this is nothing but our compound matrix variable 1, y 1, right. So, basically what we find, C 1 is nothing but phi 3 prime 0 by y 1, and C 3 we find minus phi 1 prime divided by y 1. Okay. And this is what we get, and the boundary condition, whatever we have written it down here, this part is here. So, you can now see additionally that omega dependence is there through this. Okay. So, now if we are doing this full time dependent problem, we realize that we will have to look at the alpha plane. So, if this is alpha r alpha plane, we will have to design a Bromwich contour. And what is the way that we decided that we should have Bromwich contour? That it should be either along the real axis or parallel to the real axis, because we want to use the power of Fourier transform and use that. So, what we usually do is draw a line somewhere there. Why? Because we know there are modes which go downstream and they are unstable. So, if they are unstable, that means what? And going downstream, where would those eigenvalues be in this plane? That will be somewhere in the 4th quadrant, right? Alpha is positive, alpha is negative, that is what we saw. So, this eigenvalues, if they are there, those relate to your unstable TS waves. Now, we discussed also that if we draw this as the Bromwich contour, okay, so this is my, say, the Bromwich contour in the alpha plane. Anything above corresponds to downstream propagation, anything below corresponds to upstream propagation. That is why the choice of the Bromwich contour, the location, has to be decided upon by yourself. There are no you cannot just simply say for all problem it is like this. What you have to do is you will have to do a little bit of grid search technique, find out all possible eigenvalues, refine it by using Newton-Raphson method. Once you have gotten all those eigenvalues, let us say in the last case when we looked at Reynolds number of 1000 and omega naught equal to 0.1, we found 3 such eigenvalues, right. That is what we found. Now, we need to really put our Bromwich contour below all of these 3. So, what we found basically, it is a kind of our experience, the rule of thumb, that this point could be something like your alpha equal to minus 0.02. So, basic idea is what? Whatever may be these eigenvalues, while you are performing the Bromwich contour integral, at each and every point the effect of all those eigenvalues are there. So, this is something you understand, that how different this receptivity analysis is from eigenvalue analysis, because while you are performing the Bromwich contour integral along that Br alpha that you have written, we are simultaneously getting the effect of all eigenvalues, including even also the essential singularity. That is what we explained in the last 2 lectures, that even if I were to close this up, the contribution that comes supports those delta functions, right. We did see that. So, this is a very elegant way of doing it, that once you perform the Bromwich contour integral, you get contributions of everything. So, you are not making the so called normal mode analysis. What is the normal mode analysis? You look at one eigenvalue at a time, but this is a much more general methodology that we are discussing. So, in the signal problem, we were happy with Br alpha alone. Now, in the full problem, what we need to do is we need to also worry about the omega plane also. How do you find that omega? Now, where would we position the Bromwich contour in the omega plane? Think of what we just now talked about. What we talked about, that we will have to push it in such a way that all the eigenvalues remain above, because this corresponds to downstream propagation. But look at the sign here, there is already a minus sign. So, here in this case, if I put a Bromwich contour, anything above would correspond to what happened before T minus, and if the eigenvalues are below the Bromwich contour, they will correspond to T positive. So, what we would essentially do is we will choose a Bromwich contour in the omega plane that is going to be above this. What does it mean? We have positioned in such a way that all the eigenvalues would be below it. Why can't we have any eigenvalue above it? That would be disaster physically. You understand why? Because that would correspond to that I am starting an experiment now, it has started affecting negative T. I have not even started, things have started happening in anticipation of what we are doing. This is what we call as the causality principle. So, the causality principle demands that your Bromwich contour should be above all possible eigenvalues, right. So, this is something that we do. So, basically then our experience suggests that you put it some value of 0. Well, maybe 0.1 or something, that should be adequate. However, I must admit that there are no rigorous theoretical work that has been done in this particular field to really show some necessary and sufficient conditions for identifying Bromwich contour. Some mathematicians may like to adopt such a problem and spend some time and do something. But we have now understood the scope of the full time dependent problem vis-a-vis the signal problem, and we now also understand the power and elegance of the receptivity analysis over eigenvalue analysis, right. So, this is something that we must keep in mind when we go ahead. And now, if I do this analysis, what do I get? Here we got something almost 20 years ago. I show you two results. One I called it as the full simulation, the other we term it as time asymptotic solution. So, this time asymptotic solution is nothing but the solution of your signal problem, and full simulation is this part. And what you notice that when you do the full simulation, these are shown at some distinct height. So, this is near that inner maximum we talked about, right, where the signal is the strongest for the disturbance quantity. So, that is what we see, that it goes like this, and this is for some particular time instant. When we look at the signal problem, we do not have anything to worry about time. Why? Because we expect that this thing will be all pervading. Okay, that is what we have to. But when it comes to the full simulation, it will depend on where exactly we are looking at, because with time this thing will increase. This thing will increase the stretch of the packet. So, this is going to grow like a packet and go outside, and this is a solution which is obtained at the outer maximum. Okay. So, this you can see that where they exist together, they are indistinguishable. Only thing that you are seeing some bit of difference is a phase shift, and that phase shift comes from where? Well, of course, how you start off the problem. So, that's that. I mean, I could have phase shifted the time asymptotic solution and made it match here, but we are purposely showing it next to each other so that you can distinguish. But you can really see that this is what you have, and what you notice that the signal problem indicated the combination for this case is exactly the same, r equal to 1000 and omega equal to 0.1. That solution and the full simulation solutions are identical, and that made us conclude that indeed in some instances the full simulation and the signal problem are just the same if we are looking at unstable system. And this kind of thing that we talk about will show that this kind of spatiotemporal wavefront that we talked about exists for both stable as well as unstable system. So, when it comes to unstable system, we see that the full simulation and the signal problem yields the same result. Okay. And you may be thinking that this I am contradicting myself by identifying this as the inner and this is the outer maximum, but please do note the y scale, right. This is less than 1 and these are in thousands. Okay. So, that is the kind of distinction that you get between inner and outer maximum. Well, I also pointed out that despite this, that when you come to experiments, you are more comfortable in measuring the signal at the outer maximum because of the larger range over which it exists. So, the measurements are more reliable. They are not hypersensitive to the location, while inner maximum is very difficult to track. Of course, today probably with mechanized traverse mechanism, it should be probably easy to scan it, and people can probably measure the whole stretch, not necessarily only at inner or outer maximum. Okay, so this is something we want to talk about. Next is, we are so far talking about disturbances which are generated by some excitation source being placed inside the shear layer. What happens? What happens when we look at general excitation problem? What is a general excitation problem? General excitation problem is excitation is everywhere, like what we actually encounter. Let us say we fly an aircraft. It is not necessary that flow instability is caused by, let us say, the aircraft wing vibration. That would be like your wall excitation problem. But suppose I have designed an aircraft, the wing is quite rigid, or the flight condition is such that the wing vibration is imperceptible. But then still I could have disturbances coming with the oncoming flow, like what we call as the free stream turbulence problem. If we have such a situation where we could have excitation simultaneously at the wall plus at the free stream, we want to study some such problem. Okay. So, let us say once again we are exciting the shear layer from inside by putting a vibrator at the wall itself. So, we have u equal to 0, v is non-zero, and now we have positioned the exciter at x equal to x naught, because now we see we do not have that liberty of fixing the x axis, because now what is happening? We have the excitation here as well as excitation in the free stream. So, just for the sake of convenience, we would be talking about a problem of this kind that will probably fix the x axis at the leading edge itself. So, we will be talking about this kind of a thing, that we have exciter somewhere here and we fix the origin here, and of course, y axis starts from here, and at y equal to capital Y, let us say we allow some kind of a vortex to convect at a fixed height, and that height is what we are calling as capital Y. Okay. So, that is why you notice that the wall exciter is located at a location given here x naught. Okay. So, that is the two wall conditions, that is what we had done. Now, what we are going to do is we are also going to provide a disturbance in the free stream. Now, you see what will happen. You recall that in our Orson field equation we have 4 fundamental modes: 2 decay with y, 2 grow with y. But now in this general excitation case, what we need to do? Can we throw away those 2 modes which were growing with y? Because eventually match up to this disturbance level, I cannot just stay with the wall modes, because the wall modes decay. But if I give a finite disturbance here, I must keep those other 2 modes also alive. But unfortunately, if you notice, in our eagerness to solve the stability problem, we have all along only considered wall modes. We did not even conceive of this problem. So, now what we are talking about, that we need to keep those neglected modes before, and then what happens? Then we still can do stability study. It is just that people were not careful. They were some kind of in a rush to somehow get some results, and they just simply looked at the wall mode. We can do that, and that is what I am explaining, that how you can set this problem up. So, at time t equal to 0, let us say the vortex was here, at a subsequent time it has come there, and it is going at a constant speed c. I particularly like this problem because what you are noticing, that we have in general an equilibrium flow which is steady. We are imposing a time scale by a vibrator here, and what about this vortex? This vortex is going at a constant y at a constant speed c. We will see later on that when we switch this off and we look at this problem alone, that a steady convection will excite system at imposing some additional time scale due to dispersion relation. So, this is something that we would see, that is the whole intention, that even though we look at a steady problem, we still can get unsteady solution. Now, that vortex that we saw in the previous slide, it is essentially we are studying a 2D problem. So, what is the structure of this vortex? This is a line vortex perpendicular to the board. It goes from minus infinity to plus infinity in the z direction, right. So, that is what we have. We have a line vortex at a height capital Y, and which has a strength of gamma, which convects with a constant speed c at a constant height y over the wall. Now, what happens? The moment I have that vortex, I create a flow field, a disturbance field, for which the stream function can be given like this. What do we get? This the gamma is the strength. So, gamma by 4 pi, it is a 2D flow. This is ln of x minus x bar plus this y plus capital Y whole square, and in the denominator is this. How did you get this? I purposely did not explain. I want you to help me understand what is the nature of the problem that we are talking about. So, now you see what is happening. I have a vortex here which is far outside the shear layer. So, this is part of the flow. Now, this vortex could be a viscous vortex, it could be a irrotational vortex, does not matter. The moment I place it in front of a solid wall, to satisfy the no slip condition, no penetration condition, well, there will be a slip velocity, but to satisfy that there is no net wall normal velocity, I must have a image system. So, once I have a gamma there, I should have a minus gamma here. So, that if I look at any point on the wall, this will introduce, you can connect this will introduce a velocity in this direction, and this one will introduce a velocity in this direction. So, that the wall normal component cancels and the two provides a slip velocity. You see that this is a description of the inviscid way of looking at this vortex. Okay. Now, what happens? This vortex itself moves at a constant speed c. So, this x bar that appears here will be a function of time. So, that is what it is. If my initial location is x v naught, then I will take it minus c t, so that it moves with it. And so, at any instant of time, this is the imposed disturbance field by the vortex at any arbitrary x and y. Why we are doing it? Because we are actually creating a disturbance field because of this. So, now what we do is we once again write down the disturbance plane. This is a full problem. However, we note now this one should have all the 4 fundamental solutions. This is the essential difference. Now, if we keep all these 4 conditions, well, we can still do one thing. See, like the inviscid solution corresponding to this gamma and its image gives rise to slip velocity, but still we are inside the boundary layer. We still should support a no slip condition. That is what we ensure by demanding this, that this C1, C2, C3, C4 should be such that the prime quantities, so that is del psi del y at the wall should be equal to 0. At the wall is indicated by additional subscript 0, right. Now, we have seen that we have a wall exciter. The wall exciter is determined by the magnitude V w. It is located, let us say, at x equal to x naught. It is excited at a frequency omega naught, and then we can write it like this, isn't it? So, once again I am writing it like this, I alpha x minus x naught, that is because of that shift theorem, right, because this is not at x equal to 0, but at x naught. That is why I have shifted it alpha x minus x naught. What about omega? Well, we are once again looking at the corresponding signal problem. That is why we have put it delta of omega minus omega naught. But we can also fill it up with the actual problem like what we have done here. We can do this exercise. So, what happens is in terms of Fourier Laplace transform, that v velocity condition would yield this quantity, because we are looking at del psi del x. So, del psi del x will give us I alpha times this phi. So, what we have written here is phi here, I alpha has been transported here downstream, and this is what we are getting for the signal problem. Okay. Okay. So, what happens is this is the condition at the wall. So, what we can do is we can similarly set up the other 2 conditions in the free stream. Those free stream conditions are identified with this added subscript here infinity. This is corresponding to the u velocity, this is corresponding to the v velocity. Okay. So, basically you are looking at the effect of free stream excitation through this right hand side B and D. I am just leaving it very general, but for a very specific type of excitation we can evaluate this quantity, right. We just now seen if I have a discrete vortex moving at a constant speed c, I can immediately work out what is the expression of B and D. Remember what we have written down, that expression psi infinity, that is for the disturbance quantity, right. That is why we are matching those disturbance u and v with respect to this equation 98 and 99. Now, if we have done this, what we have here is essentially 4 equations for the 4 unknown constants C1 to C4. Okay. So, that is when we write it down, we can write it down in a linear algebraic relation like this. Some matrix phi operating on this unknown vector C1 to C4, and this is our forced excitation, right. This is our forcing, that is what we have given. The first 2 comes from the wall condition, the last 2 comes from the free stream condition. What happens? Well, I can immediately obtain Ci C1 to C4 as phi inverse times this, right, phi inverse times the excitation in the spectral plane. So, you notice that immediately you can smell the eigenvalue problem because of the existence of that phi inverse, because what it would involve? It would involve in the denominator a determinant of phi matrix, right. So, that is how we actually solve the wall excitation problem earlier too. There we did not do it for 4, we did it for 2 constants C1 and C3. So, here we are generalizing. So, the moment we do that, we can immediately see that the phi matrix comes from this. You can clearly identify the first row corresponds to the u velocity component, right. That will give you phi 1 prime, phi 2 0 prime, phi 3 0 prime and phi 4 0 prime. The second line corresponds to your wall exciter, the v velocity, that will be in terms of phi 1 0, phi 2 0, phi 3 0 and phi 4 0. What about this too? Well, this is a good news, because we already know the analytical structure of the solution far away from the wall. We know the analytical solution for the 4 modes of Orson field equation. What we find that they are these, right. One is e to the power minus alpha y, the other one is e to the power plus alpha y. Here the third component is e to the power minus q y, the fourth component is e to the power plus q y. Earlier what we did, in the presence of wall excitation alone, we just knocked this 2 part up and we were looking for those 2 solutions. Now, this corresponds to your u velocity, right. I differentiate it with respect to y and obtain the quantity at capital Y. This is what we get. It is pretty good. You see now what happens. We are not trying to solve the problem, we are trying to understand what happens to our dispersion relation in this case. And this dispersion relation will come from where? Where the determinant of this phi matrix is equal to 0. And this is just what we said earlier, that this is q square is this, and these are obtained from the properties of the Orson field equation given earlier. But the characteristic determinant or the dispersion relation is obtained by putting the determinant of phi equal to 0. This is actually the story. Rest is all details. So, once you obtain this, then we can work it out. Now, how we can obtain modes? Now, what has happened? You see, when we are looking at solutions in the alpha plane, now earlier so far we have somehow kept quiet about the left half plane. We have all along talked about the cases where alpha are equal to 0, the alpha is greater than 0. Why? Because we are looking at wall modes, and if we are trying to find out the waves that go in the positive direction, downstream propagating wave, then alpha r has to be positive, because that is what we get. If I scale out alpha r here, then I will get x minus c t. But now what happens? Because we are keeping all the 4 modes alive, we cannot just simply talk about only this part. We will also have to talk about I minus I of alpha r x. So, we are basically talking about the modes or eigenvalues which could be here. It is interesting, if you look at many research papers, well, not many, one of the paper by Ashpish and Reshotko, and the book by Smid and Henningsen. Smid and Henningsen actually reproduces that figure from Ashpish and Reshotko, where they try to show this portrait, and they say this with a question mark. I mean, are they there or not? They are not very sure. But our discussion very clearly shows that we could also have eigenvalues on the left half plane. So, how do we locate those eigenvalues for which real alpha is negative? That is, we are looking at eigenvalues in the left half plane. And if there are eigenvalues on the left half plane, where would they go in terms of the phase? They will go upstream, right? Well, please do not misunderstand me if I say that you look at the phase and decide whether it is going upstream or downstream. To do that, we have to again recompute the group velocity and make sure that they are indeed going upstream or downstream. And you also be very, very careful now in talking about the value of alpha I for which you will have stability or you will have instability. Why? Simply is this, that if you are looking at a upstream propagating wave, now alpha I should be what? If it is to grow, alpha I should be positive. So, this is just a complementary picture. So, you look at the sign of alpha I and you also calculate the group velocity, and then you make up your mind about which eigenvalue corresponds to what. But in general, we are talking about that there is a possibility that we will have upstream propagating mode and we are in the lookout for that. So, we are looking out for real alpha is negative. Why do we do this part? You see, Q has been always obtained from a algebraic relation, and when I compute it using a computer, I always get the plus part, and I know there is a plus part and there is a minus part. That is what we are. So, suppose we do this, we are now trying to find out what happens. Now, as y goes to infinity, this capital Y goes to infinity, what happens to phi 2 and phi 3? If my alpha is now negative real path, then this will decay, this is also is going to decay. So, these two phi 2 and phi 3 are now the decaying modes, whereas phi 1 and phi 4 will be the growing modes with y. So, basically then what we are in essence saying that phi 1 and phi 4 will support the applied free stream excitation, whereas phi 2 and phi 3 will support the wall excitation boundary condition, right. This is what we need to appreciate and keep at the back of our mind. So, now you see what happened. We are looking for modes in the left half plane. So, what happens here? What we had? Here we had alpha e to the power plus alpha y. So, if I talk about y going to capital Y going to infinity, this actually goes to 0, does not contribute. Same thing, this also does not contribute. Same thing about here. Now, what happens? We are in the lookout for determinant of phi, and this is the structure of phi for modes on the left half plane. So, we are actually looking out for the eigenvalues in the left half plane. So, now we have gotten. So, you work it out. You work out this expression. Now, it is very easy. You can expand it probably using the last row, and then you get this. You get this. Please work it out and convince yourself that you will get the determinant is equal to minus of alpha plus q e to the power q minus alpha to y and into this. And you see the dispersion relation is uncannily resembling what we had earlier also. Earlier also we had the same dispersion relation constructed out of the decaying modes. Here also phi 2 and phi 3 are decaying modes. So, it is a sort of a very fortuitous occurrence that I could use the same code and I could locate the eigenvalues in both the right half as well as left half, and I will get both the modes. In fact, tell you a bit of a storytelling. When I was in one of the leading UK university, I located some of these eigenvalues and I talked to the person with whom I was working. He said, use Whitener, because he cannot explain what it is. But now you can see, we can explain everything today to our satisfaction, that if we do identify using the same code, eigenvalue also on the left half plane, they will correspond to those waves for which the phase is propagating upstream. So, when we are talking about upstream propagating mode, we are basically talking about phase propagation of upstream, and then we can use the same code and we can obtain this. So, this question mark is unwarranted, and this is what we did about 15 years ago, and we published a paper, and what we found out was completely accidental. This is what I always like to say is serendipity of research. You start looking for something, you look for a worm, you dig up a snake. So, this is what actually happens. What we are looking at, we were trying to look at a completely different problem. You recall that when the German school was proposing all the stability theory, the English school was trying to oppose it. Why? Because G.I. Taylor performed an experiment. What he did, he took a boundary layer and then he created some wall exciter, and he did not see any wave, and then he pronounced that Tolman-Schlichting waves do not exist. It is only a theoretical artifact. I did the experiment and it is not there. But what G.I. Taylor overlooked, or no one pointed out to him at that point in time, is the frequency. He used a sort of a circular patch which was vibrated at a very low frequency, less than 5 hertz. Whereas Tolman and Schlichting's calculation shows waves, the stability curves show the waves to be in the moderate range in terms of, say, more than 10 hertz or so. Now, what happened is we wanted to really see what happens, because we were also intrigued by another paper by that same professor from that leading UK university. They also repeated G.I. Taylor's experiment, and they also reported exactly same findings, and they just came out with observations saying that for very low frequency waves, instability is not there, but there is no explanation. So, we were interested why it is not there, we wanted to explain. Now, let me just clean up the blackboard and show you how we proceeded with the problem. The problem was simply this. We were looking for the eigenvalues. So, what we do is, let us say we plot on this axis. Maybe I have some figure. I think I will just jump to that figure and show it to you. Here it is. If we say plot say on this axis omega r, and on this axis in the top figure I am plotting alpha r, and the bottom figure I am plotting alpha I. Now, what happens is, suppose I am looking at a problem of Reynolds number of 1000, and this value is let us say 0.1. We know there are 3 eigenvalues, okay? 1, 2 and 3. Okay? Please note that there is a alpha r equal to 0 axis. So, on this side you have positive, below you have negative. Now, what happens is that is the value we have obtained for omega r equal to 0.1. So, what we started doing is keep reducing the omega naught and then see what happens to these 3 modes, and we saw that they keep going like this. For example, this what we called as the second mode in the previous table, when we came down to this value of omega r, it just simply disappeared. So, we did that grid search. At these values we only found 2 eigenvalues, one corresponding to this, one corresponding to that. We further went on reducing it. Then after this we found that there is only one eigenvalue. The third one also has disappeared. We keep doing it, keep doing it, keep doing it, and come up to here. And beyond this, we have no eigenvalues. And this is exactly what that paper in physics of fluid was talking about, that there are no theories if your frequencies are too low, because you cannot do that. But then I recall that 20 years ago, I did find some modes, and I find that that mode is this. So what happens is, after this, I do actually have a mode. Corresponding alpha I curves are like this. So these are all positive, and we can show from the group velocity they are also positive. So they are all decaying modes 2 and 3, while the 1 is slightly negative, because your alpha I equal to 0 axis remains slightly above this line. So it remains unstable for some frequency, then it becomes stable, and before disappearing it go in there, and this one we get it there. Now you see what has happened. This remains negative throughout. So when we first found out, we were worried, because alpha I is negative, alpha R is negative. So what does it mean? Well, of course, then you do is calculate the group velocity and ensure what it is. And since we are talking about here the properties of gaseous boundary layer, so what you see is this, and this is basically a chart which shows those 3 modes one by one disappeared, right? The third mode disappears for r equal to 1000 at this value 0.0276. The second mode disappeared earliest, right? That was around 0.0663, and the first mode also disappeared when omega naught is reduced to 0.0026. You can actually convert these values into hertz, and there it would be. So and this was the physics of fluid paper that reported for a Reynolds number of 1196. We will start from here in the next class.